Chapter 5: Management Functions and Reference Models: Getting Organized. This chapter picks up right where we left off in our discussion of management dimensions in the previous chapter. Specifically, it takes an in-depth look at the function dimensions of network management, a big topic that deserves its own chapter. This concerns the range of functionality that management applications and operational support system need to cover. We discuss these functions along the lines of several management reference models, which do a great job of organizing these functions. Reference models are conceptual frameworks introduced for the purpose of organizing in a systematic manner the different functions of a system or a technology network management. In this case, after reading this chapter, you will be able to first explain what the most established functional reference model FCOPS stands for and what it consists of. Second, outline the wide range of management functions in network management and explain these functions entail. Third, describe the OAMP model, an alternative functional reference model that is popular with telecommunication service providers. Third, explain the limitations of reference models. And lastly, describe how different functional reference models relate. Of pyramids and layered cakes. As mentioned previously, management reference models serve as conceptual frameworks for organizing different tasks and functions that are part of networking management. The emphasis is on the word conceptual. In reality, reference models are, in many cases, not literally followed. Management systems and operational support environments can be structured in different ways that, for various reasons, do not reflect the same breakdown in functionality as suggested by any particular reference model. However, a reference model can be used for guidance and helps provide a sense of orientation in the following ways. It makes it easier to check a management system or operation support infrastructure for completeness. It forces the person applying the model to differentiate the different tasks that must be addressed. For the reference models presented here and for the purpose of this chapter, this aspect is the most important. Second, it helps categorize and group different functions and identify which ones are closely related. Third, it helps to identify scenarios and use cases that need to be collected and to recognize interdependencies and interface between different tasks. Use cases are a part of use case analysis, a software engineering methodology that is used to derive functional requirements for a system by analyzing in a systematic manner different ways in which the system might be used, hence the term use case. A few reference models have been widely established. One of them is the fault, configuration, accounting, performance, security model, commonly referred to as FCAPS, pronounced FCOPS, rhymes with snaps. As its name indicates, it divides management functions into 5 categories: fault management, configuration management, accounting management, performance management, and security management. It is actually part of a larger management reference model that we introduced in the previous chapter, the TMN reference model. As mentioned earlier, the TMN reference model covers much more than just management layers. The FCOPS categorization of management functions is one of the concepts that it introduces. We can withdraw the TMN pyramid from figure 45 with more refinement, as in figure 5:1, to show the functional dimension in addition to the layering. Whereas the layering dimension of the TMN model was discussed in the previous chapter. This chapter takes an in-depth look at its functional dimension. Another reference model is the operations, administration, maintenance, and provision OAM and P model. Here, management functions are categorized a bit differently. Ironically, although the FCOPS model originated from TMN and was intended to standardize network management for telecommunications, large telecommunication service providers traditionally favor the OAMP model. We take a look at this model as well. Although these are the most prominent reference models, they are not the only ones. Network management can be organized in 1,000 ways. Still, discussion of these reference models teaches important lessons regarding established ways to think about network management. Even more important for the purpose of this chapter, discussing reference models provides a great opportunity to explain in detail the different functions that are associated with managing a network. TMN and similar models are sometimes criticized as being overly complex, looking like multi-layered cakes of many slices when perhaps a donut would do. However, in many cases, much of this criticism stems from an important understanding of what these models are all about. A number of points should be kept in mind when considering reference models. First, a reference model is conceptual, that is, an abstract partitioning of a problem space. In general, there is no need for an actual system to follow the structure of a reference model literally. Second, a specific application or operational support system may be designed with very specific constraints in mind. A reference model, however, has to be generally applicable and cannot be optimized for any one specific case. Otherwise, there would be a risk that the model might break in other scenarios. That is, the model might lose its generality. Third, generally, it is advantageous to be able to slice up a problem space for many of the same reasons that make component-based systems more attractive than monoliths. Different functions can always be combined later. Breaking up is what's hard to do. FCOPS, the ABCs of management. To get handle on the wide range of management functions that are required in an operational support environment, people often group them into a set of broad categories that are known as fault, configuration, accounting, performance, security, FCOPS. This is categorization that we use to go over various functions. In many cases, functions categories can be addressed independently of each other in terms of both systems supporting them and the organization performing these functions. For instance, fault management activities such as monitoring, diagnosing, and troubleshooting devices are very different in nature from configuration management activities that deal with the configuration and turnout of devices. The subsection that follow introduce each of the FCOPS function categories in more detail. The subsections contain a number of enumerations that might appear lengthy, but that are intended to convey the breadth of the spectrum of functions associated with the management of network systems. The functions are presented mainly from a user perspective, functionality that is at the disposal of a service provider, organization, and network management within that organization. F is for fault. Fault management deals with faults that occur in a network, such as equipment or software failures, as well as communication services that fail to work properly. Fault management is therefore concerned with monitoring the network to ensure that everything is running smoothly and reacting when this is not the case. Effective fault management is critical to ensure that users do not experience disruptions of service and that when they do, disruption is kept to a minimum. Fault management functionality includes, but is not limited to, the following. First, network monitoring, including basic alarm management as well as more advanced alarm processing functions. Second, fault diagnosis, root causes analysis, and troubleshooting. Third, maintaining historical alarm logs. Fourth, trouble ticketing. And lastly, proactive fault management. Network monitoring overview. Network monitoring includes functions that allow a network provider organization to see whether the network is operating as expected, to keep track of its current state, and to visualize the state. This functionality is fundamental to being able to recognize and react to fault conditions in the network as they occur. The most important aspect of network monitoring concerns the management of alarms. Alarms are unsolicited messages from the network that indicate that some unexpected event has occurred, which in some cases requires operator intervention. Those unexpected events can actually be about anything, from a router that detects that one of its line cards is no longer working, to, literally, a fire alarm, from a sudden drop in signal quality on a wireless link, to a suspected intrusion into the network by an unauthorized user. Like other alarms in real world, an alarm in a network might actually set off a bell just like a fire alarm, or result in automatic dispatch of operating personnel, similar to alarms set off by some intrusion detection system. In most cases, however, they simply result in a message being sent to a management system, which lets an application or an operator decide what to do. Alarm management is such a large area that the term is sometimes used synonymously with fault management, although there is more to fault management than alarms. Alarm management includes many functions that we classify into basic functions, such as alarm collection and visualization, and more advanced functions that involve processing alarms to perform filtering and correlation tasks. Basic alarm management functions. We start the discussion of alarm management with the more basic functions: collecting alarms, maintaining accurate and current lists of alarms, and visualizing alarms and network state. The most basic and at the same time the most important task, the task that everything else builds on, consists of simply collecting alarms from the network and making sure that nothing important is missed. This includes receiving the alarms and storing them in a memory so that they can be further processed by an application or a human operator who decides how to react. Basic alarm management functionality also includes persisting alarms, that is, writing them to disk or storing them in a database to build historical records of alarms that occurred. In more sophisticated cases, alarm collection can include additional, more advanced mechanisms that can check that no alarms were lost and that can request replay of alarms, as long as the network provides such capabilities. In practice, alarms can be lost in many ways, even when this is not supposed to happen. After all, in most cases, the event that is being alarmed was not supposed to happen either. For example, the underlying transport might not be reliable, and the alarm information might thereby be dropped on the way to the management application. Another reason alarm information might fail to reach its destination is that the network is congested and alarm messages simply cannot get through. Remember that this situation was one of the selling points for a dedicated management network. In a third scenario, the alarm information might actually have reached the host of the management application but was still not properly collected because the application or database was not functioning properly or was being restarted when the alarm message arrived. After alarms have been collected, an accurate list of current alarms needs to be maintained. This list answers the questions: which current conditions in the network require management attention, and which issues are currently being experienced with the services provided by the network. The alarm list also informs the operator of the current state of each of the various entities that are being managed and whether a particular device, for instance, is having problems. To maintain the alarm list, it is not sufficient to simply append alarms to the list as they occur. Alarms can also clear, that is, the underlying condition that causes the alarm can be resolved. The current list of alarms needs to be updated accordingly, removing alarms when they no longer apply. It is also important to understand how the alarms and indeed the network states are visually presented to the user. In its most basic and important form, visualization can occur simply through textual lists. Those lists can be searched, sorted, and filtered according to many different criteria, such as alarm severity, the type of alarm, the network element, or range of network elements affected, the type of network element affected, the time of day when the alarm occurred, and many more. However, visualization can occur in many ways. One popular method uses topology maps. Icons on the map represents devices and can be animated to indicate the current alarm state. The alarm state corresponds to the highest severity of any alarm condition on a device, of which there might be several. Likewise, connections can be represented on the topology map as indicated by lines that connect the icons. Like the icons, the lines can be animated with different colors to indicate the current state of that particular connections. Not all alarms indicate a complete failure of a device or the services running over it. In fact, in most cases, they do not. The severity of an alarm indicates the degree of impact of its underlying condition. The higher the severity, the greater its impact on the network, services, and end users. For example, red might be used for devices on the map with a critical alarm, orange for major alarms, yellow for minor alarms, and green for no alarms. Gray might be used to indicate lost management connectivity to the device. Please note that red would be inappropriate in the case of lost connectivity because the device itself might in fact be functioning properly. Of course, icons can be used not just to represent individual devices, but to present groupings of devices that can be zoomed into. In that case, the color for the grouping of devices reflects the most severe alarms of any of the devices contained within it. Topology maps can make monitoring systems look attractive and hence become good sales tools for those systems. In addition, they provide a good overall picture of the wealth of a network and a good way to indicate geographical hotspots and identify where the real problems lie. If everything in area Chicago suddenly turns red, including the single access router through which all those devices are connected to the core network, chances are the resolution for the problem lies with that router, and that's where the troubleshooting should start. As figure 5-2 illustrates, this way, the graphical representation of topology on a map makes information much easier to correlate than if the same information were merely represented in a flat list of alarms interspersed with alarms from other parts of network. Many reasons exist for maintaining historical alarm data in addition to the list of current alarms. This requires simply logging and archiving alarms as they occur, which is actually simpler than maintaining the current list. After all, items are appended only at the end of the list. Historical alarm data is not required for monitoring the network but is useful in many other ways. For example, historical alarm data can be mined to help with future diagnosis and correlation when we come to these topics in a moment. Basically, this can be helpful to identify alarm patterns that have occurred in similar form on past occasions. Recognizing such patterns and recalling their past resolution can help resolve future problems faster. Second, it can be used to establish trends to see how alarms rates and types of alarms reported have evolved over time. Last, it can be analyzed in conjunction with other historical data, such as changes that have been performed on a network, for example, the introduction of new network elements and its impact on historical alarm patterns, or correlation of alarms with certain usage patterns of the network.
Advanced alarm management functions. Beyond those basic alarm management functions, in any network of meaningful size, additional functions to manage alarms are required. Some of those functions provide network managers with greater flexibility in processing alarms. For example, an alarm forwarding function might send alarms to the pager of the operator to allow for an automatic dispatch. Much as home intrusion, detection systems automatically calls the local police station. Another function allows network operators to acknowledge alarms, meaning that they confirm that they have seen the alarm and are taking care of it. The functions might allow network operators to open a trouble ticket. A third function handles the clearing of alarms is recognizing when alarm is no longer current, or more precisely, matching failure onset and failure remission conditions. Most alarms have underlying alarm conditions. An alarm message is sent to the report to onset of this alarm condition. At some later point in time, a second alarm message might be sent to indicate that the alarm condition no longer exists. It is important to maintain at the management system level accurate list of the current or standing alarm conditions without needing to query the network device for what those conditions are. More often than not, the device does not have such a query capability. Besides, it would be a bad idea to continuously poll the device for information that can be derived from information that it has sent already. You can think of the alarm conditions in terms of the conceptual panel of light-emitting diodes or LEDs, one each distinct alarm condition that exists on the device. The left side of the diagram depicts a chronological list of alarm messages. Some messages indicate the onset of an alarm condition of a certain type. Others indicate the remission of the same condition. The alarm has cleared. The list of the current alarms include only those messages that have not cleared. That is, those for which no matching clear indication has been received. The right side of the diagram depicts a fictitious LED panel that indicates which of the alarm conditions are current corresponding to the alarm list. When an alarm is cleared, it means that the underlying condition that caused the alarm has ended. This is different from acknowledging an alarm. Acknowledging merely means that the alarm was noted and, presumably, action is being taken. To use a physical picture, if the alarm sets off the bell that keeps ringing, turning off the bell corresponds to acknowledging the alarm. The problem might still be indicated by a LED that is still lit and that will remain lit until the underlying condition that caused the alarm ends. Only at the point will be the alarm be cleared. Another category of function that is related to managing alarm concerns trying to reduce the amount of the information that human operators and higher level management applications are exposed to. It is possible in a large networks such as those of large telecommunication services providers for hundreds of thousands of alarms to occur per day, so many alarms that alarm processing capabilities of alarm management applications are often measured in hundreds of alarms per second. Of course, not every alarm indicates sometimes major or an impending catastrophe of its own. Most are not really alarms in the narrower sense of the word, but event messages. Still, they need to be looked at. The problem is therefore how to reduce the volume of the information that must be evaluated. Generally, two techniques deal with the potential event information overload. One technique is filtering. Its goal is to remove event information that is deemed unimportant or redundant, to allow the receiver to focus on the more relevant event information. The other is correlation. Its goal is to pre-process and aggregate data from events and alarms and distill into the more concise and meaningful information. Alarm and event filtering. Let us first turn our attention to filtering, not just of alarms, but of events in general. To focus on operators or management's applications attentions on those events that really matter, it is important to block out of as many irrelevant or less important events as possible. This is analogous to the way in which the human brain is able to deal with the massive flow of the data that is constantly exposed to, such as sounds, visual images, and sensory data. To focus, it filters out massive amounts of data that would be otherwise be distracting, for example, background of noise when following a conversation. Another way to filter alarm concerns the duplication of alarms. In some cases, the same alarm condition might cause the same alarm to be sent repeatedly because each new instance of the same alarm contains no new information. The new instances might simply be thrown away. The process of discarding the redundant alarms is referred as deduplication. A similar scenario in which the considerations apply is that of oscillating alarms. In that case, there is an underlying oscillating alarm condition, causing alarms to be sent and then cleared again immediately before occurring again in rapid succession, multiple consecutive times, although oscillating alarms relate to only a single condition and hence relatively easy to spot. They can lead to a high overall alarm volume that drowns out other events that are happening in the network. Therefore, the alarm should be turned off. Fault diagnosis and troubleshooting. Alarm management is a significant aspect of fault management, so significant, in fact, the two terms are often used synonymously. However, there is more to fault management than alarms. One other aspect concerns fault diagnosis and troubleshooting. Diagnosis is often supported by troubleshooting functions. Troubleshooting can involve simply retrieving additional monitoring data about a device, data that was not conveyed as part of the alarms. In addition, the capability to inject tests into a network or a device for troubleshooting purposes provides essential support for diagnosis activities. Network diagnosis is conceptually not much different from medical diagnosis. The difference, of course, is the type of the patient. To reach a medical diagnosis for a set of symptoms, for example, rash, the doctor might want to take a look at additional monitoring data, for example, by taking the patient's temperatures and blood pressures, and might conduct his or her own series of tests, such as testing the reflexes or asking the patient to breathe deeply while listening with a stethoscope. Proactive fault management. Most fault management functionality, such as alarm management, is by nature reactive. It deals with faults after they have occurred. However, proactive fault management is also possible, that is, taking steps to avoid failure conditions before they occur. This includes, for instance, the previously mentioned injection of tests into a network to detect deterioration in the quality of the service and impending failure conditions early, before they occur. Proactive fault management can also include alarm analysis that recognize patterns of alarms caused by minor faults that point to impending bigger problems. Trouble ticketing. Trouble tickets are one way in which a network provider organization can keep track of the resolution of network or services problems that are typically require human intervention. Those problems might have been reported by a network itself through a certain types of alarms, or they might have been reported by a customer experiencing a problem. When certain problems are encountered or reported by users, a trouble ticket is issued to describe a problem. Trouble tickets are assigned to operators who are responsible for resolving the trouble ticket that is taking care of the problem. The trouble ticket system helps keep track of which trouble tickets are still outstanding. It can automatically escalate a problem if it is not resolved in time. The system can also help communicate problems between different operators by automatically attaching the entire history of the problem and its resolution to the trouble ticket.
C is for configuration. We now turn to the second letter in FCAPS, C, which stands for configuration management. For the network to do what it's supposed to do, it might need to be first told what to do. That is configure. This is similar to having to initially set up a VCR so that it tunes to the proper channels. To select the proper input for connections from a video console, a later needing to program the VCR to record a particular show. We dive into configuration management functions in more detail in the following subsections and cover the following topics. 1. Configuring managed resources, whether they are network equipment or services running over the network. 2. Auditing the network and discovering what's in it. 3. Synchronizing management information in the network with management information in management applications. 4. 4. Backing up network configuration and restoring it in case of failures. 5. Managing software images running on network equipment. Configuring managed resources. At the core of configuration management are the activities and operations used to configure what is being managed. Ultimately, this involves sending commands to network equipment to change its configuration settings. In some cases, this involves only one device in isolation, such as configuring an interface on a port. In other cases, configurations operations that are performed on the devices are simply part of bigger operations at the network level that involves changing the configurations of multiple devices across the network. An example is getting up a connection across the network, such as a static route or an ATM permanent virtual circuit or PVC. Auditing, discovery, and auto-discovery. Being able to configure your network is important but not enough. You need to also be able to query the network to find out what actually has been configured. You need a read in addition to the write. This is referred to as auditing. Many reasons exist for auditing your devices in the network. For example, you might want to verify that the configuration of the network is indeed what you expect it to be. You might want to see if configuration commands that you send down indeed took. Without this function, a service provider would have a very hard time understand what is going on in a network and why it is going on. Synchronization. Each time you or your management applications needs to know your network configuration. You do not want to first have to audit the equipment or discover the network. That would be much too inefficient and slow. Instead, you expect your management system to maintain a cache of information about your network, probably stored in a database. At least, this is the case for information that is relatively slow to change, such as which equipment is deployed in the network and how it was being configured. After all, configuration information is not the same as state of statistical information that rapidly changes, in which case you have no choice but to retrieve it on demand when you need a real-time view. Depending on which view is taken, one of the following functions is used to synchronize management information. Reconciliation. The network is considered the master, and the information of the management system should reflect what is actually in the network. Reprovisioning. With reprovisioning, the management system is the master of management information. Synchronization flows from the management system to the network, resulting in configuration changes to network devices as needed to that they reflect the information in the management inventory. Management information reflects the network as planned. Discrepancy reporting. With discrepancy reporting, discrepancies are simply detected and flagged for the users. The management application does not make a decision about the direction in which synchronization is to take place. Backup and restore. If you are a PC user, you are aware of the importance of protecting your data by performing regular backups. You never know when your hard disk will bite the dust or whether your PC will contract virus that could destroy your PC file system. Having a backup of your data in such cases enables you to recover. With the backup in place, contracting a virus or needing to replace your hard drive is still annoying, but if bits by far simply wipe out. Likewise, the need for backup and restore functionally applies to the network. Here, your user data is not Word files or Excel spreadsheets, but the configuration data of network. This data is very critical and needs to be protected. Just what you protected, the accounting data and customer database of your company. Imagine you some cas- Capalic event taking down a portion of your network and wiping out configuration, possibility affecting thousands of users or customers. Image management. As with PCs, network equipment vendors occasionally issue new software revisions. Such revisions might be new features releases, or they might be simply be patches that contain bug fixes. In these cases, you need to be able to upgrade your network. The problem is that now you are not dealing with a single PC but with hundreds or thousands pieces of equipment scattered across your network. To do so effectively, you need to be able to keep track of which software images are installed on which network devices are and have a way to deliver new images to network devices, where to upgrade appliances and install them without disturbing service. A is for accounting. Organizations that offer communication services over a network ultimately need to generate revenue for that service they provide. After all, this is how they make their living. If they do not bill for the services they provide, they will not stay in business for too long. Notwithstanding, some dot-com business that might give a service way to compensate for it to some other means such as advertisement. P is performance. When you buy a car and look at different choices, you assume that the cars when you are looking at can all transport you from a point A to B. Each of the choices might also offer automatic transmission, power door locks, air conditioning, and perhaps a navigation system. However, those functional properties alone might not be tell the whole story, and you might even take them for granted to make a decisions. You also to take a non-functional properties, most important of which is performance. Does the car accelerate from 0 to 6 mph in 5 seconds or in 25? Performance metrics. Some examples of performance metrics are these: throughput, measured by a number of units of communications performed per unit of time. The units of communications depend on the layer type of network and network service in questions. Examples are as follows. At the link of layer, the number of bytes or octets that are transmitted per seconds. At the network layer, the number of packets that are routed per seconds. At the applications layer for a web service, the number of web requests that are serviced per seconds. That applications at the layer for a service that network of voice call or call attempts that can all process per hour. Monitoring and tuning your network for performance. Performance management deal with monitoring and tuning your networks for its performance. This includes a wide variety of functions at the most basic level, you want to able to retrieve snapshots of the current performance. This corresponds with taking a look at the speedometer of your car to see how fast you are going. Of course, in this case of network managements, the speedometer is replaced by package counters, delay measures, and outlets that increase utilization percentages. For a more subtle analysis, you might want to be observed of these parameters over time. For example, you might want to plot a histogram of some performance values on a screen with a new sample taken every seconds or every 5 minutes or whatever time interval suits you.